Alrighty, lots of ladies. Welcome back to Calc 2. I will be getting started here in just 1 second. Sorry, I'm a little behind this morning. All right, here we go. On with coffee. We are ready to get started. Okay. Go ahead and turn on the screen share. We can get things rolling. I think I'm a little bit behind on updating you guys' video links in Canvas. So just going through and taking a look. Trying to get caught up on those. So I will have the rest of these from 24 on posted in the next few hours. But if you did miss that and you need to go back and rewatch that stuff, it'll be there soon. My pre-calculus class is learning how to factor polynomials with synthetic division, which is a fun thing. But you guys are doing something even more fun today. We are going to start learning about series. Last time we talked a little bit about sequences. There's a little bit more I want to say about sequences before we dive in full hog to the series stuff. So we'll start with just a few extra results on sequences. I think last time we finished with a couple of theorems, and we didn't have the opportunity to play with all of those theorems as much as we would like. So let's start with that. Of course, this is MAC 2312, section 004. That means we're talking about Calc 2. And the date today is the 6th of October, 2021. I'll tell you right now, I am a little bit behind on grading your tests, but I am working on it. We're getting there. I had some issues with the testing center, and it looks like not your class, one of my pre-calculus classes, we had some cheating going on in the testing center, and that is tying things up. So I'm working on it. I promise they'll be done very, very soon. And as soon as I get them done, I'll be entering the scores as we go. So I'll ask you to be patient with me as I wade through this quagmire of bullshit. I promise you it'll be done as soon as possible, very soon. Today, we are going to finish sequences, which was section 11.1, and we're going to begin series in section 11.2. So on Monday, I did post your new homework. Your new homework has a bunch of sequence stuff and a bunch of series stuff. The series stuff, there are going to be several sections on series, like 11.2 through 11.8 or so is all about just basic series stuff. So 11.2 and 11.1 are the foundations for everything we're going to be doing in the rest of chapter 11, especially 11.2. Really need to be comfortable with that stuff, the notation and everything like that. Just so I have a feel, right? Same as I asked you about sequences the other day. Go ahead and take a second to locate your reacts in Zoom. Give me any sort of react, thumbs up, whatever, if your pre-calculus class discussed infinite series at all. Like summation notation. Whoa, okay. So pretty much everybody had seen sequences, but only a couple of us got to see series at all in pre-calc. That is a motherfucking shame. You know that? That's the best part of pre-calc. Okay, that's all right. That's all right. We'll pick it up from there. So Sequences, last time I gave you a few theorems. We didn't get to fuck with them very much, so let's fuck with them a little bit. Let me pop open your textbook just to make sure I'm not missing anything. Oh, come on. Okay. So we had the notion of a limit. Of course, all the limit rules from Calc 1 hold. These are the last few theorems we were talking about. So we had this theorem. We have the squeeze theorem, which is the same as the squeeze theorem for functions. Have this theorem on continuous functions that you can shove a limit into a continuous function. We need to talk about geometric sequences and monotone sequences. So let's say recall. We have this theorem which says that the limit as n goes to infinity of the absolute value of an is 0, then the limit as n goes to infinity of an itself must be 0. This is actually a special case of the squeeze theorem. It's also a special case of our theorem on continuous functions, where you take the continuous function to be the absolute value function. But sometimes it's useful on its own to just think of it like this. We did have one sequence last time where from the graph, we were able to tell that the limit was 0, but we didn't have any algebra tools that told us what the limit was. This theorem will give us a path. Let's find the limit of the sequence. An equals -1 to the n plus 1 over n squared. N obviously starts at 1, so on. Right, so this was like the second sequence that we graphed on Monday. And from the graph, we were pretty convinced that the limit was 0, but we haven't seen that for sure yet. So from the graph, which we saw last time, we think that the limit as n goes to infinity of -1 to the n plus 1 over n should be 0. By the theorem, it suffices, right, is sufficient, it suffices to show that when n to infinity absolute value of -1 to the n plus 1 over n is equal to 0, right? Because if the absolute value goes to 0, so does the original sequence. So if this is true, then this is true, right? And it's that logic that is so important here in chapter 11, making sure you're comfortable with the logic of the theorems. The way we're going to do this, the way we're going to show that this is true, is by working with this absolute value. So let me show you some rules for absolute value. First off, the absolute value of a product, if you have two things multiplied inside, a and b here could represent whatever you want, numbers, functions, variables. That is the product of the absolute values. Similarly, the absolute value of a quotient is the quotient of absolute values. And finally, if you have a power in absolute values, that's the same as the absolute value of that base raised to that power. Those are three very important algebra rules for the absolute value function. It is a fully multiplicative function. So what I'm going to do now is use these rules for absolute value to clean up this expression until I know how to take the limit. So the limit as n goes to infinity of the absolute value of -1 to the n plus 1 divided by n. By that first rule, by the second rule, is the limit as n goes to infinity of -1 to the n plus 1 over the absolute value of n. Absolute values split up nicely over multiplication and division. Downstairs here, the absolute value of n, since n is going to positive infinity, remember n, the variable we use for sequences, is always positive, right? We never use a negative value for n in the sequences. The domain of the sequence is either 1, 2, 3, and so on, or 0, 1, 2, 3, and so on, none of which are negative. So downstairs, the absolute value of n is just n. Copy the parts that don't change, then n to infinity, fraction law. Downstairs here, I now just have n. The absolute value of n is just n. Upstairs, I can use the third rule. The absolute value of -1 to the n plus 1 is the same as the absolute value of -1, all raised to the power of n plus 1. All right, so powers pop out of absolute values as well. What is the absolute value of -1?
1.
1. So this is when n to infinity 1 to the n plus 1. Now forget about the limit for a minute. What is 1 to the n plus 1 for any integer n? If I take 1 and I raise it to a positive
1.
Yeah, I always get 1. So this limit is actually the limit as n goes to infinity of 1 over n. And that's a limit we know, right? What is the limit as n goes to infinity of 1 over n? See it in chat maybe? Very good. Yeah, it's 0, right? 1 over infinity, which is 0. So the limit of the absolute value of my sequence is 0. Therefore, by the theorem, then n to infinity 1 to the n plus 1 over n equals 0 also. So the 1 over n limit here being 0, this isn't something we should have to think too hard about. There's a theorem from Calc 1 which you may or may not remember. I'm going to restate it here in terms of the variable n. The first time you saw this, it would have been in terms of the variable x. When n to infinity, 1 over n to n power r will be 0 if r is positive. All right, so if you have the reciprocal of a positive power, That will always go to 0. You can find this down back in section 2.6. They just used the variable x back then. Questions on this guy? Okay. What would be wrong about me saying I'm going to take the limit of the top and the limit of the bottom here separately? What is the limit as n goes to infinity of -1 to the n plus 1 on its own?
Infinity over infinity.
So here, what I'm trying to do is cut off a few. Let me go this off. A few common errors. Then n to infinity, -1 to the n, or then n to infinity, -1 to the n plus 1. These guys do not exist. Because they just bounce back and forth between plus and -1. Because -1 to the n has a graph looking like this. And -1 to the n plus 1 looks the same. When n is 0, he's equal to +1. When n is 1, he's equal to -1. When n is 2, he's equal to +1. When 3, he's equal to -1. And 4 is equal to +1. So these dots are not getting closer and closer and closer to some horizontal line. And -1 to the n plus 1 looks the same thing. It's just shifted a little bit to the left by 1. A few other limits that people tend to goof up a little bit. When n to infinity sine n, when n to infinity cos n. These are also not infinity. They're not 0. They do not exist as well. For essentially the same reason. Sine n and cos n bounce around from -1 to 1. When you plug in integers here, you don't get nice numbers. You're not going to get 1 out of this ever, or -1, or 0 out of this ever. But you will get just a bunch of shit bouncing around along the graph of sine, or a bunch of shit bouncing around along the graph of cosine. So common errors here, these things. Be careful with those. Right, so if you have a sine of n or a -1 to the n or something like that in your sequence that you're trying to take the limit of, you're probably going to need something like the theorem we just used, or the squeeze theorem, something along those lines. So be careful with that stuff, please. Please be careful with that stuff. Okay. What else do we want to talk about? The squeeze theorem for sequences is the same as the squeeze theorem for functions. I don't see a need to really beat that stuff to death. We talked about L'Hopital's rule. And they talk about -1 to the n being a divergent sequence here, which is good. They approach this guy, which I just did. The continuous function theorem we looked at by looking at sine 1 over n. I think it'd be good to get a little bit more practice with factorials. The particular example in here that they're using is a little gnarly. So let me give you something slightly more tractable. Determine whether the sequence, and I'll write it like in the braces notation, n factorial over 2n plus 2 factorial, and we'll say n goes from 1 to infinity, converges or diverges. If it converges, state the limit. All right. So what do? I've got a sequence. I want to know whether it converges or not. What question am I trying to answer? How else can we phrase this? So I'm not asking for the answer. I'm just asking where should I start?
Write it out as a limit.
Yeah, if I want to know whether a sequence converges or diverges, I need to know whether the limit exists or not. Does it have a finite limit or no? So remember, what it means for a sequence to converge is that the limit as n goes to infinity of that sequence exists and is finite. That's the definition. So this is what I need to look at. Now the objects in question here are weird, right? It's got this exclamation point. Who remembers what the exclamation point means?
Factorial.
Good. So what is the thing in the top, n factorial?
1 times 1, 2 times 1, 3 times 2 times 1, so on until infinity.
Almost. So remember, for any particular finite number, n factorial is a particular finite number. So like what you were listing there, you were listing specific factorials, right? Like 1 factorial is 1 times 1. 2 factorial is 2 times 1. 3 factorial is 3 times 2 times 1. N factorial in general is n times n minus 1 times n minus 2, all the way down to 3 times 2 times 1. So when you're trying to simplify, remember last time I gave you some problems to look at with factorials. When you're trying to simplify a ratio of factorials, you should just write them out. And the definition of anything factorial is the product of all the positive integers less than or equal to that thing. So the factorial of n is 1 times 2 times 3 all the way up to n. And we usually write it in descending order like this. I recommend always writing the first few terms and the last few terms. Don't just like skip, don't just write n and 1, because you want to see how the cancellation works when you do stuff like this. So n factorial, the top, that's the easy part. What about 2n plus 2 factorial? What would be the first term in 2n plus 2 factorial?
2n minus 1 plus 2.
That sounds like the second term. So I think the first term in anything factorial is that thing itself. So I want to multiply that number by the number right below it. What's the number right below 2n plus 2? What's the next smallest integer under 2n plus 2?
2n minus 1 plus 2.
2n, so it'd be 2n plus 2 minus 1. You take that thing and subtract 1. In other words, it would be 2n.
Oh, from the whole thing or from the n?
From the whole thing. Yeah, from the whole thing. So because the factorial is on the outside here, right? That's the idea. So we're taking the factorial of 2n plus 2. If it was 2n factorial plus 2, then that would be like what you're saying, or close to it. Be maybe a little different, but so it's this number times the next smallest number times the next smallest number. So the next guy here would be 2n. And it wouldn't be wrong to say this goes down to 3 times 2 times 1. That would be okay. But here's a question, who's bigger, n or 2n plus 2?
2n plus 2.
Definitely 2n plus 2. So as I run down this list from 2n plus 2 all the way down to 1, in particular, what number is going to show up? So my next number here.
Sorry, what was the question?
So the next term here would be like 2n minus 1, right? As I go down, right? Subtract 1, subtract 1, subtract 1. Eventually, I'm going to get down to n itself. Right? The term right before n would be n plus 1, and then n minus 1, and then n minus 2, and then eventually we'll come all the way down to 3 times 2 times 1. So here's the bottom written out. That's 2n plus 2 factorial written out. Yes, exactly, Prashant. N factorial will eventually show up. This piece right here is n factorial. And we can cancel it with the n factorial upstairs. So this ratio, n factorial over 2n plus 2 factorial, cancels a lot. In fact, like half the terms cancel. And what I end up with here is lim n to infinity 1 over all the stuff that didn't cancel, which is 2n plus 2 times 2n plus 1. And I'll just go all the way down here, we'll say it like this, to n plus 1. So that denominator, after you cancel everything, is the product of all the numbers bigger than n and smaller than or equal to 2n plus 2. All right. So I want to take a second and ask, how comfy are we with this? Writing out of factorials? I know it's a little bit strange the first few times you see it.
I'm not really sure how you go back to, like, how did you get rid of the 2n? How did you get rid of the 2?
I haven't. These terms are still hiding in the dot dot dots here. I just didn't write them.
But on the right side, like, how did you end up with n factorial to cancel it out?
So 2n plus 2 is bigger than n, and 2n plus 2 factorial is the product of all positive integers less than or equal to 2n plus 2. So because n is smaller than 2n plus 2, there will be a copy of n factorial hiding inside of 2n plus 2 factorial. So what I'm doing is I'm just trying to understand what 2n plus 2 factorial looks like. And what we realize is that within this big product where I'm multiplying all the numbers from 1 up to 2n plus 2 is this product where I'm multiplying all the numbers from 1 up to n. So this is all the numbers from 1 to n. This is all the numbers from 1 to 2n plus 2. And because between 1 and 2n plus 2 is n itself, the whole product of n factorial shows up inside of 2n plus 2 factorial. We can look at I'll look at another one of these, perhaps a slightly simpler one of these next, because it seems like this is still feeling a little bit wonky. But the big idea here is to try and see what's in the denominator. The thing that's running in the background is if m is bigger than n, then there is a copy of n factorial within m factorial. That's sort of the nice intuition here. So if you're comparing the factorial of two numbers and one of the numbers is larger, then the factorial of the smaller number will be hiding inside the factorial of the larger number. Like 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. And 3 factorial is 3 times 2 times 1. So that last 3 terms, 3 times 2 times 1, inside 6 factorial is 3 factorial. So just to finish things up, each one of these terms downstairs goes to infinity. So this is definitely 1 over infinity, which is 0. Let me look at a slightly easier example, since I feel like I may have lost some of you here. Let's just simplify n factorial over n plus 4 factorial. So the factorial of n is n times n minus 1 times n minus 2, all the way down to 3 times 2 times 1. The factorial of n plus 4 would be n plus 4 times the number right beneath him is n plus 3 times n plus 2. And what I realize here is that because n plus 4 is bigger than n, I expect to find a copy of n factorial hiding in the denominator. I can actually write this out. These are close enough that I can actually write this out. The next term here would be n plus 1, and then n minus 1. And we see it, n minus 2, all the way down to 3 times 2 times 1. You see right here. Is my copy of n factorial hiding within n plus 4 factorial. And I can cancel. So everything here is being multiplied. We can cancel those. And so what we would get is just 1 over n plus 4 times n plus 3 times n plus 2 times n plus 1. Everything else canceled.
Okay, I see it better now. What was throwing me off was the multiplication of 2 and n. So that would still go away. You would always end up with like the smaller with n factorial.
Yeah. So eventually, as you walk down from 2n plus 2 all the way down to 1, between 2n plus 2 and 1 is n. So somewhere, if we're looking back at this first example, as you walk all the way down from 2n plus 2 to 1, and that's what 2n plus 2 factorial is, right? It's the product, multiply, all the numbers less than or equal to 2n plus 2. Because n is smaller than 2n plus 2, as we walk down, eventually we will hit n. And that's what I was trying to communicate here. So we just go down 1, go down 1, go down 1. Eventually, we will get to n plus 1. And then after that would be n. And then after that would be n minus 1. So eventually, we will come down to n. And everything n and beneath is n factorial. So this absolutely takes some practice. It's not something you've seen before, unless you've taken a really good statistics class. And yeah, this will be kind of magical the first few times you see it because you're learning a new notation. But once you practice with it, it'll feel quite natural.
How much do we have to write on the denominator before we cancel out?
That's a good question.
Because on top we have like the dots.
So my advice is to write out as much as you need to be 100% confident that you know exactly what is there. So if I wanted to, I could have said 2n plus 2 dot 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 n plus 1 and n minus 1, right? I could have skipped writing all this shit. But I wrote these first few terms here to make sure we were comfortable with how this product was started. And also I knew I was going to cancel all the n factorial stuff. So I wanted to, know what to write after we cancel.
And if the top factorial is less than the bottom factorial by like any number, it's always going to cancel out completely, the top one.
Yep. Yeah, exactly. And that's the blue statement here. So the factorial of a larger number always contains the factorial of the smaller number. So like hiding within 10 factorial is a copy of 9 factorial, is a copy of 8 factorial, is a copy of 7 factorial, and so on. And think of the factorial as like a box that has all the numbers from 1 up to that thing. And so of course, that box would contain all the numbers from 1 up to anything less than that. So this is just playing with notation. I would love to spend more time on it, but unfortunately, it's something that it's just a part of Calc 2. You have to practice this on your own a little bit. And I really want you to get comfy with factorials because again, they're going to be super important as we work with series, which is almost where we're ready to go. So I'm going to move away from the factorial stuff for now. I've got one more really important theorem for you in section 11.1. All right, one more thing that doesn't come from Calc 1. And that's geometric sequences. Does anybody know what a geometric sequence is? My people who had a good sequence treatment in pre-calc?
Is it exponential?
Yeah, that's perfect. I love it. That's exactly how I like to say it too. These are the sequence version of exponential functions. I.e., what that is, a sequence an is geometric if it can be written in the form. I always like to start my geometric sequences at n equals 0 if it can be written in the form an equals a times some constant r to the n. And here I'm assuming n starts at 0. Your textbook sometimes starts these at 0, sometimes starts them at 1. The life is much nicer. The notation is cleaner if you start them at 0. Right? So just like f of x equals c times b to the x is your general exponential function, an equals a times r to the n is your general geometric sequence. Here, a and r are constants. The number r, constant r, is called the common ratio. And that common ratio is what's going to determine the behavior of your geometric sequence. So maybe what I'll say here for a second is recall exponential functions have two types of graphs. according to whether they are growing or decaying. The ones that we're most familiar with, like e to the x, have a graph that looks like this, right? This is a growing exponential. This is the graph like f of x equals c times b to the x, where b is bigger than 1. So if the base is bigger than 1, you've got a growing exponential. The other way these can look is like this. This would be like f of x equals c times b to the x, where b is less than 1. These are called decaying exponentials. Your kind of prototypes are e to the x and e to the negative x, right? E to the x has a graph that looks like the one on the left. E to the negative x is the same as 1 over e to the x and has a graph looking like on the right. Remember what we said about sequences, right? Sequences can be thought of as dots along the graph of the continuous function. So if when you replace n by x, you get a continuous function, which we do here, then the sequence can be thought of as dots along this graph. So the behavior of a geometric sequence is going to be determined by the size of this common ratio, R. Before I dig any deeper, let me just look at an example or two. So let's write the first 5 terms of the sequence an equals 3 times 1/2 to the n. And again, I'll assume n starts at 0. So those first 5 terms would be a0, a1, a2, a3, and a4. A0 would be 3 times 1/2 to the 0, which is 3 times 1, which is 3. A1 would be 3 times 1/2 to the 1, which is 3 times 1/2, or 3/2. A2 would be 3 times 1/2 squared, which is 3 times 1/4, or 3/4. A3 would be 3 times 1/2 cubed, which is 3 times 1/8, or 3/8. And A4 would be 3 times 1/2 to the 4, which is 3 times 1/16, or 3/16. And observe that to go from one term to the next term, we're multiplying by a constant. This is the other way to define what a geometric sequence is. To go from here to here, you multiply by 1/2. To go from here to here, you multiply by 1/2. To go from here to here, you multiply by 1/2. And to go from here to here, you multiply by 1/2. So that number 1/2 is the common ratio. And you can see that from our definition and this formula, right? This is A times R to the N. So the common ratio is R equals 1/2. And if you look at the graph of this sequence, I'll just show you in Desmos. Oh no, Desmos sucks with sequences. Do I have a... I made a thing for sequences in Desmos. Let me see, am I signed in here? Oh, yeah. And I have stuff for series. Standards between curves. Partial sums of series, but no, not for sequences. I guess I could use this. This is going to be for later. Nah, this will just confuse you now. All right, we'll come back to that. We'll just graph this thing by hand. So the graph here I mark this as up here as 3. A0 was 3. A1 is 3/2, which is 1.5. A2 is 3/4, which is 0.75. A3 was 3/8, and I'm already running out of space. A4 was 3/16. And you can see that this graph looks like dots along a graph like this, right? Really just the part from 0 onward, but the next term, A5, would be 3/32, which I can definitely not really fit on my y-axis. A6 would be 3/64. You can see what these dots are doing, right? They're starting to pile up on the horizontal axis, on the n-axis. So from the graph, it appears that the limit as n goes to infinity of 3 times 1/2 to the n is 0. And indeed, that's true, because to go from one term to the next, we multiply by 1/2, meaning this height gets chopped in half every time you take a step to the right by 1 unit. So you take a step to the right by 1 unit, that height gets chopped in half. Take a step to the right 1 unit, that height gets chopped in half. This thing is going to 0, and it's going to 0 very quickly. So the question is, what is it about this geometric sequence that makes the limit 0? And what kind of geometric sequences would have a limit other than 0?
That it's decaying. So if the common ratio is greater than 1, then it's growing exponentially, and if it's less than 1, then it's decaying.
Perfect, you nailed it. So it's all about the size of the common ratio. The following.
What if you add like a +1 to the exponent?
That would not change things. That would not change things. So one way to get rid of a +1 to the exponent is to shift the index. Say I'm going to start at 0 instead of 1, then you can get away without that +1. Another way to think of it is that you can take like 1/2 to the n plus 1 and write that as 1/2 to the n times 1/2. So then it's just the 1/2 to the n term that dominates. 1/2 on its own is a constant. So here's our theorem on geometric sequences. The limit as n goes to infinity of r to the n. See, I don't care about the constant a, right? A constant multiple isn't going to affect the limit. It depends only on r. And there's actually some cases we should consider a little bit carefully here, because it's not quite as simple as exponential functions. Remember, with an exponential function, the base always had to be positive. But r, your common ratio here, is allowed to be negative. That's not a problem, because we're not plugging in, we're only plugging in integers for the variable. So here's the result. That limit will be 0 if the absolute value of r is less than 1. There's the boring case. If r is exactly equal to 1, and then the limit does not exist if the absolute value of r is bigger than 1, or if r is equal to -1. The r equals -1 case we already looked at. That's -1 to the n. That was that blue sequence we looked at the very start. We're going to use this later when we talk about series. Okay. So, new problem. Let's find a formula for the nth term of the sequence. And I'm just going to list some terms here. -2. Positive 2/3. -2/9. Positive 2/27. That's enough. You can figure it out from that, and so on. And then after this, let's then find the limit. Okay. So what do you notice about this sequence? What patterns do you see?
It's got to be an odd exponent.
I don't think the parity of the exponent comes into play here, but there is something to do with oddness somewhere, although it's not terribly important to the problem. Let's ask the obvious question. Does this look like a geometric sequence?
Yeah.
Yeah. What's the common ratio to go from here to here? What do I multiply by?
-1/3.
Very good. All right, we multiply by -1/3 to go from here to here. What about from here to here?
Same thing, -1/3.
-1/3, yep, and so on, right? So what's the common ratio for this geometric sequence?
-1/3.
So this is a geometric sequence with r equal to -1/3. All right. Can we find a formula for the nth term? Looks like A0 is -2, A1 is positive 2/3, A2 is -2/9, A3 is positive 2/27. What would be the next term? A4.
-2/81.
Very good. -2/81. So here's what I would do. I would say this is -2 times -1/3 to the 0. I'm just trying to see it in the form of a geometric sequence. This is -2 times -1/3 to the 1. This is -2 times -1/3 squared. This is -2 times -1/3 cubed. This is -2 times -1/3 to the 4th. So it looks like AN is -2 times -1/3 to the n, where n starts at 0. And the limit as n goes to infinity of -2 times -1/3 to the n is going to be what?
0.
0. Yeah, by the theorem above, right? Because this is geometric. And the absolute value of r is the absolute value of -1/3 is +1/3 is less than 1. All right, that's it. So this is a convergent geometric sequence. The limit is 0. There was a question a minute ago, what happens if you change the exponent to like n+1 instead of n? Well, if I had -1/3 to the n+1, then I would just rewrite that as -2 times -1/3 times -1/3 to the n. So you can use your normal algebra rules here. All the algebra that you've known since antiquity is useful in sequences as well. All right. Let me see, is there anything else we want to do with geometric sequences before I start talking about series? Monotone sequences, bounded sequences. You know what? I don't think I'm even going to hit you guys with this because we don't use it anywhere else. It's really not helpful here. I want to focus on the stuff that you need. You don't need that. I'm going to try to demystify sequences and series a little bit. So that's it. That's everything you guys need for sequences. I really do hope that you're feeling a little bit comfortable with them. Remember, you can look at their graphs. Desmos is not great for graphing sequences, but Wolfram is pretty good. You can graph sequences with Desmos. It just requires a little bit of care. I'll explain this graph to you in a minute. But if you want to graph a sequence, Wolfram's really good at it. Like -2 times -1/3 to the nth power. I can ask for the graph. Oh, it's giving us a continuous function graph sequence. They're always changing this thing. No, it doesn't like that either. All right, that's a shame. Wolfram used to be good at this. Yeah, it can be done in Desmos, but it's messy. I guess Desmos is the main tool now. Yeah, here we go. So you can take something like this, you just put in your, they use the continuous variable. So 2 times 1 to the n. And if I zoom out a little bit, you'll see the first few terms of the sequence. And they get very close to 0 very quickly. Let's play it in one direction. Let's zoom way the fuck in. There you go. You see pretty much right away, the terms of this sequence get so close to 0, you can't even tell them apart from 0. That's enough on sequences. Let's start talking about series. This is still section 11.2. And I want to introduce this with a little discussion of summation notation, which we're definitely supposed to learn in pre-calc. You used it in Calc 1 when you talked about Riemann sums, but I think a lot of people are a bit afraid of it. So let's talk about the Greek alphabet. What's this letter?
Sigma.
Yeah, this is a capital Greek sigma. Sigma. It makes the S sound in the Greek alphabet. The lowercase sigma looks like this. This guy, because it makes the S sound, that's why, stands for the word sum in math. Similar to, anybody know where the integral symbol comes from? What letter does the integral symbol look like?
S.
It's an S. It's literally an S, right? The integral symbol is just a stretched out Latin S, our alphabet. The alphabet we use in English is the Latin alphabet, similar to this, which is a Latin S. The integral also stands for the word sum. In math, this means continuous sum. And the Greek sigma means regular sum. So continuous sum is a complicated notion. It's called integration, right? And you've actually learned a lot about that over the last year or so. The capital Greek S, sigma, is used for summation in the sense that you usually think of it like 1 + 1 is 2. So what this means, if I have some bounds here from A to B, and then some stuff inside here, this means the sum of that stuff as the variable, which will usually be n, runs from A to B, very similar to your integral. So for example, and you'll see my sigmas get a little bit sloppy. If I write sigma n from 1 to 3 of 1 over n, this is just a shorthand for the addition problem 1 over 1 plus 1 over 2 plus 1 over 3. Right? I'm taking 1 over n and I'm adding it up as n goes from 1 to 3. In this case, yeah, I mean, we can compute this if we want. I don't even give a shit. I'm not even going to write it down. Fuck it. Who cares? What does matter is that you understand that this thing is just a shorthand for this thing. You can change the letters around. The sum from k equals 0 to 4 of k squared plus 1 would be 0 squared plus 1 plus 1 squared plus 1 plus 2 squared plus 1 plus, what did I say, 4, right? 3 squared plus 1 plus 4 squared plus 1. And I'm sure any of you could clean that up, right? This is just 1 plus 2 plus 5 plus 10 plus 17. You figure out what that is, right? It's not hard. The challenge arises is to understand these things kind of like improper integrals, where the upper bound is infinity. In fact, it's almost exactly like an improper integral. The analogy runs so deep that we'll later have a theorem connecting the two. Here's how we're going to do this. Right? Obviously, if the upper bound here was infinity, I'd have 1 over 1 plus 1 over 2 plus 1 over 3, but then it wouldn't stop. 1 over 4, 1 over 5, 1 over 6, 1 over 7, and it would go on and on forever. That is and I need you to pay very close attention now. What does it mean to say, I'm going to add up, for example, the sum from 0 to infinity? I'll start with an easy one. How about 1/2 to the n? And like I said, the trick is to think of it the same way you think of an improper integral. The first and most intuitive thing is to say, well, this is 1/2 to the 0 plus 1/2 to the 1 plus 1/2 to the 2 plus 1/2 to the 3, and so on forever and ever. There's no like thing at the end of these dot dot dots. This just goes on forever. Obviously, there's issues there, right? I don't have the time, and neither do you, and neither does anyone or any computer to actually add up all infinitely many terms, because we have finite lifespans. So we need to be clever about it. The trick: treat it like an improper integral, like a type 1 improper integral. I would say that the sum from n equals 0 to infinity of 1/2 to the n, and here's the first place people get a little confused. I'm going to use the variable n in 2 places. So in the second place, I'm going to use a capital N. Your textbook does this really unfortunate thing where they use a lowercase n for both. With an improper integral, I would say limit r to infinity integral from 0 to r. Here, I'll use capital N and say limit capital N to infinity, sum 0 to capital N. In terms of symbols, this is appealing, right? If you just replace this with an infinity, then it looks the same as this. But what's more important, this is an infinite sum. Which is hard to work with. Whereas this is a finite sum, which is easier to work with, right? Just like the regular proper integral is easier to work with than the improper integral. There is a name for this thing. it's called a partial sum. And there is notation for it. I'll show you the general notation, but let me just say this would be then, so what we're going to do is we're going to find a formula for this thing. We call this thing capital S sub n. And again, this is where your book fucks up. They use a lowercase n for both of those things. Don't do that. Use a capital N for your partial sums. Where S sub capital N is that sum, the sum from little n equals 0 to capital N of whatever you have inside is called the capital Nth partial sum. So remember, like we had AR, A sub R was the area from 0 to R for your improper integral. The integral from 0 to R is like your partial integral. Here, this thing, the sum from 0 to n, is the sum or series version of that thing. All right. An infinite sum like this is called a series. And what we're really doing is we're taking all the terms 1/2 to the n and adding them up. So I'm now going to show you the general definition of an infinite series and what it means for an infinite series to converge. We're going to be messing with these things for a little while. And you really, really need to take this seriously. It's not easy. But I promise you, if you invest the time to both practice the computations and think deeply about what's going on, you'll not only find that it's manageable, but it's really beautiful. Today, we are going to come back and find the value of this sum. We're going to find the value of the full infinite sum, and I have a bad joke that goes with it. Bad jokes are awesome. All right, so this is our little intro to series. Definition time. People get a little fucked up here because we're going to do something with a sequence. We're going to use a sequence to form the series, and then we're going to use another sequence to define the series. So,
Professor,
yes.
we're out of time. I don't know if you want to hold this for the next
really
class.
All the way out of time already? Shit. All right. Yeah. Okay. We'll pick it up here on Friday. That's fine. Sorry, I get excited. This stuff is good. Let me write down this. How out of time are we? Just barely. Okay. Let me write down your definition here. So, given a sequence AN, we can form the series, and I'll call it S for series, capital S, sigma n from wherever, I'll use 0 of AN. This is the sum of all the terms of the sequence. So instead of a list, you're adding up all the things in that list. By defining S to be the limit as capital N goes to infinity of the finite sum. And again, that finite sum we usually refer to as S sub n, where S sub n equals sigma little n from 0 to n of A sub little n is called the partial sum. Of the series S. Okay, we say the series S, the full infinite series, converges if that limit lim n to infinity Sn exists and is finite. That is, the sequence of partial sums is a convergent sequence. This is a fine place to end. So, given a sequence, you can form a series as the sum of the terms of the sequence. The way you define that big infinite sum, it's a problem, right? You can't just say I'm going to add up infinitely many things because it takes too long. It's infinitely long. So you define it as a limit of a finite sum. That finite sum, Sn, is called the partial sum. Sn is itself a sequence. You feed in a number capital N, and this spits out a number. So we say that the big infinite series converges if the limit of the Sn's exists and is finite, which you recognize right here, this little blue box statement is exactly what it would mean to say that the sequence Sn is a convergent sequence. All right, I will let you ponder that. You can take a look at some of the homework problems that involve infinite series. And on Friday, we will dive deeper. All right, Friday, that's good. It's a lab activity. That's a lab day. I've got some lab stuff for you to do. So make sure you show up on Friday. We're going to be looking at a bunch of cool shit. Again, this is the hard part of the class. So please take it seriously and invest the time now. It will pay off so much down the road, not just through the rest of the series stuff, but when we talk about power series, very, very important. So I'll let you go here. Thank you guys for hanging around a little bit later, and I'll see you all on Friday.
Do we have office hour at 1 today?
I do. Yep. Normal office hours. Bye, guys.